Oh, hello again. Right, so you've already heard me speak. So let's start our presentation with this image that many of you have seen before. A famous picture and quote for Henry Ford, and the quote being, if you'd asked people what they wanted, they would have said faster horses. Now, many people, Steve Jobs and others, had said similar quotes about other technology developments. And of course, in this picture, what Henry Ford is talking about is the transition to the car. But what he's really talking about is education. And it's hard for people to really understand the art of the possible unless you can show them. And that's why it's on us as industry and this community to show people, not just tell people, the art of the possible when it comes to digital twins, and we need to do so through tangible applications.
So here's the title of the presentation today, Decarbonizing the Energy Sector with Connected Digital Twins. My name is Tortora, and I head Innovation Strategy and Digital Transformation over at National Grid, Electricity System Operator.
And I'm Simon Evans, if you haven't already been here for the last half hour and heard me speak.
So yes, this is not a last-second entry to Eurovision. We're actually doing this presentation, the two of us, a bit of it to wake up conference. Realize this is the graveyard shift, but mainly because we're each here to speak about different aspects of the program. I'm here on behalf of National Grid ESL, and I'm here to tell you about a problem, really, that we're facing. You're aware of the fact that the energy system is decarbonizing. You probably heard this 100 times today, and what it means for decarbonization. What it means when you're decarbonizing a system is pretty much that you're transitioning from your, normal thermal, I usually like to say smelly, noisy thermal generators to lighter, cleaner sources of energy, which is what the cool part of decarbonization looks like. Now, as a utility, we deal with the bill at the end of the day, the problems that arise from decarbonization. So what does it mean for us to take you to a net zero future? So you got your target by 2035, you have to be able to operate the system when it's net zero. It means that today we're running a system that can go 30%, 40% renewables. Tomorrow, by 2035, we're looking at net zero. So that's a 70%, 75% or higher penetration of renewables on the system. We're looking at, from the latest numbers that we've gotten, about 78 gigawatts of offshore generation. That is 1.5 times our peak demand right now in the UK, just about. So you can imagine what that means for us. We're looking at increasing our interconnector capacity from about 4 gigawatts to 18 to 30 gigawatts, and what that means with our relationship in Europe and how we coordinate each other. And finally, in order to deal with all of this, we're going to have to find somewhere, somehow, about 20 to 30 gigawatts worth of flexibility. This number keeps changing. Every time you get a new FES published, that number goes up. It's not going down. So that means that we need to find a way to run the system in such a way that we can provide up to 30 gigawatts of flexibility nowadays. So how do you do that? How do you find 20 to 30 gigawatts of flexibility? And again, that comes with a few caveats. Number one, you have to keep costs down, right? Because if I could cover the whole country in batteries, I would have already done so, and I would have my 20 to 30 gigawatts of flexibility and everyone will be happy. You can't, right? So what you have to do is you play a margins game. You got to find flexibility where you can, however you can. So you do that by looking at a whole system, an integrated energy system. Where is that flexibility coming from? Who's going to give it to you? You need to know everything at once. In order to get an integrated energy system, and what you get from it ultimately, is the ability to run a whole range of scenarios involving different components of the energy system. So what would happen if demand goes up like this, while at the same time you're getting your interconnector power going down? What happens if Putin decides that he wants to invade Poland too? And what would happen to our generation at that point? What can you rely on? Where are you going to find that generation? What happens if you have, I'm not going to say the name, but there's actually a word that describes very low wind periods of time. It's a German word as usual. What happens when you get no wind? Those 78 gigawatts of wind go down. How are you going to find that generation? You need whole scenario thinking. To get those scenarios, the data for those scenarios, you need visibility. So that's where we came from, right? So we understood that we needed to see things that we'd never seen before. You needed to understand things that you never bothered with before. And there you go.
And to get visibility, of this complex system with its dispersed behaviors, you fundamentally need data sharing. Now, what we mean by data sharing is that's sharing of information between organizations, cross organizations, or even cross sectors in a secure and resilient way. Now, that's not just about sending emails to each other, because that's not really going to work. It's about that machine-to-machine integration, that interoperability between different systems that will enable that data sharing. And in order to gate data sharing, as you've probably heard said a few times in this conference, we fundamentally require a common framework, which is both social-technical in nature, to facilitate that interoperability. Now, when we say social-technical, the technical aspects, obviously things like modeling, taxonomies, the physical hardware, the stuff that often gets the focus. But the social aspects, things like policy, regulatory, legal, skills, is the area we often don't emphasize, but is as, if not more, important than the technical side. But both have to be done together. Now, from this diagram, we could, of course, complete the circle further and conclude that in order for us, as society and humanity, to achieve net zero, we fundamentally require a common social technical framework to facilitate interoperability. Now, if you agree with our conclusions here, which I hope you do, then what you'll see we're coming up with and the solution is something that I hope will excite you.
So that was really the idea, right? So that's where it came from. We need to create a virtual energy system. We need to ensure that we, as ESO, we enable, we empower the system to develop an ecosystem of connected digital twin for the whole of GB. This will help us and the rest of the system solve wider challenges, such as optimization, carbon reporting, investment planning, net zero transition, and so on. So we're not building a single digital twin of the energy system. That's never been the intention. We're just creating a framework where you can connect a federation of digital twins. And I'm sure this has sound familiar to a lot of you after the day today.
So kind of building on that language, and again, the theme of this being the Connected Digital Twin Summit, the idea of an ecosystem of connected digital twins is probably pretty familiar. And of course, in the context of the energy system, we have our digital twin representation here, a physical digital asset connected in two ways. And this, of course, being a wind turbine. But we know a wind turbine is part of a system. That system, of course, including transmission, distribution, and obviously the consumer at the end. And each of these systems, of course, in the real energy system is connected by physical wires, the electricity system as it exists. And of course, being the energy system being diverse and dispersed, we also know that each one of these different entities is a separate legal entity, a separate owner-operator. And therefore, it's logical to assume that each one would have their own digital twins, answering their own questions. Now, of course, here, as we know from this summit, this equation isn't balanced. You're missing something. You're missing that bottom line, that connectivity through these digital twins, that digital connectivity layer, that layer of interoperability, or fundamentally, what is being provided by the virtual energy system. So what are we trying to do and how are we going about it? So we started talking about this. We launched it actually at COP26, so we're talking almost 2 years ago. From the first time that we started having these conversations, the questions that we were getting were always, why? Right? That sounds like a great idea, but why? So we realized that we couldn't just be preaching the word here, we needed to prove value. So that's why the whole program is actually built around use cases. So you start by showing what the outcomes are, what the benefits will be, and then once you hook them with the use cases and the benefits, then you start talking about, okay, so to enable these benefits and these use cases, this is the data that needs to be shared. You try to make this as light, as small as possible. You create that fabric of data sharing. And in order to enable all of this, of course, you need intense stakeholder engagement. So there you have it. Those are the 3 work streams. You got one around the use cases, one around identifying what are the data sets that need to be shared, and one around engaging the right people, the right stakeholders at the right level, and ensuring that you get the right governance in place for it. So as Carolina was just saying then, how do we make this happen? Well, a big part of this is the common framework. So we did some thinking, we consulted with other connected digital twin programs around the world, and realized there's a number of principles or factors that need to be considered in order to make all of this a success. Now, we grouped those into 4 categories: people, process, data, and technology. And in each of these categories, as I say, there's a number of factors, indeed 14 of them. Each of them is equally as important as the next, all of them required to make this a success. So to unpack these for you, of course, we're starting with data. So we looked at what data is really required here. What are the factors around it? Around aligning those models and taxonomies, applying the right management and governance around data, increasing the visibility and sharing of that data, and of course being security-minded from the outset. Now, to have this data, of course, you need the supporting processes. So it's about aligning with the existing standards and codes that there are in industry, because again, this isn't about repeating or creating anything new, it's about using what's there and leveraging it for success. It's about engaging stakeholders and making sure we've got everyone involved in the conversation, and of course defining the operating environment and the governance framework. Now all this of course is fundamentally supported by people having the right skills, the right training, the right knowledge, the right roles and responsibilities defined, and of course the right culture. And finally, the technology, the more known aspect, understanding what that means and how it can integrate with the system. Now, of each of these equals, 6 of them were prioritized and what the team are taking forward to develop first. And all of this is being done through the lens that you've probably heard mentioned a few times in this event of collaborate on the rules, compete on the game. Now, the purpose of this and what this statement means is that we realize that we have to collaborate as industry on what is and isn't included in these factors. So once the rules of the game are created, we, as industry, can then compete on that game based on our own commercial interests and drivers. Because, of course, we are a markets organization, a market sector, after all, and we have to realize there is commercial entities and commercial operation at play.
So here are some of the use cases. I don't want people to think that we've only identified 3. There's actually dozens, as our head of VES portfolio will probably tell you. These are some of the high-level ones that include the most data sets I'd like to discuss. The first one, for want of a better name so far, is the Common Framework Demonstrator. What we're looking at building here is the very first digital twin of the distribution and transmission system exchange. So digital twin is a model of something. In this case, it will be exactly what the distribution system needs to see from the transmission one and what the transmission needs to see from the distribution. Hopefully, by the end of this program and when we finished building this, we'll be able to identify what data set needs to be exchanged to what standard, how frequent, and so far. It would enable us in the control room to have visibility of the right things to make the right decision. This would save a lot of money for the consumer, but it will especially make the experience of all customers at the grid much better one. Our second one is CrowdFlex. Now, CrowdFlex is the first of its kind because it's a huge program that's attempting to actually build a digital twin of something we've never done before, which is demand. Demand for a transmission system operator or an ESO is a very big thing, right? So usually our smallest step is about 500 megawatts, which is Oxford. So we don't really know or care about your car charging. We won't see it because it's like, what, 3 kilowatts, 7 kilowatts? It's an abat-jour in your house, so we don't really see it. But the future, however, sees us having, as I said, it's a margins game. So we will need to care. We need to know what's going on because that's 50% of the market. You can't possibly afford to ignore it. So we need to build some sort of model twin of how this behaves. To do that, we need data. That's CrowdFlex. CrowdFlex is trying to explore and build data sets that will allow us to start building that very first digital twin of demand in the UK. This, of course, will enable huge flexibility access for ESO, but it will also help us in reducing those bills going forward. We've predicted that it's about at least a 15 to 20% reduction of bills if it works the way it should. Finally, dispatch optimizer transformation. Sorry, it's called DOT. It's not my choice of words, but this is another world first and it's super cool. This is the project that we started designing with Google X actually a couple of years ago. And it's looking at revolutionizing completely the way the control room works. So very shortly, the way that the control room works today is our control room engineers have to make decisions minute by minute in real time. Every time they have to make a dispatch decision, they're presented with this is the actual situation right now, and these are the services that you can access. You then have to choose the cheapest one. So we have to stay technology agnostic, so you always pick the cheapest option. The problem with that is that, of course, a sequence of cheaper options does not necessarily result in the cheapest overall pathway at the end of the day. The moment you've picked one resource, automatically the others, you're essentially the casino. Everyone is trying to play the house here. And so everyone will know that that cheap resource is gone. The prices will go up. So you will necessarily have to make a more expensive decision on the next time the choice comes in. So we're turning this checkers game into a strategy chess game, where we're trying to create scenarios that are looking ahead and saying, what would happen if we made this decision? Telling you ahead of 3-4 moves so that you know what the best way is to go forward. Today, our control room engineers are going through this whole process in their minds. And this was okay when you had about 140, 150 GSP that you had to choose from. But in a future where you have hundreds of thousands of renewable sources across the country, that's just too much to expect. So we got two options. Either we fill the control room with thousands of engineers, or we figure out a way to really leverage digital twin technology and AI to come up with a better solution. And that's where the Dispatch Optimizer Transformation Program that is trying to look at AI, working in combination with the digital twin, connected to the VES system, so accessing real-time data to make the best possible choices for the system. And that is really it. Please reach out to us if you want to get involved. We do have stakeholder groups in all three areas that we just discussed. So the data framework piece, where we're looking at all of your data geeks. Anybody who's got any ideas of technology, please reach out. We've got a use case advisory group. We are looking at other use cases. I was in Europe last week. They're starting their job exactly now, the same thing that we've been working on now for about a couple of years. Their problem is that they cannot think of a single use case. So we're ahead of them in that. We have seen the value, and we are building upon it. And then finally, of course, for the people and process bit, because even though it doesn't sound as cool as the other two, we do need to start identifying what the right governance structure, what the right regulatory approaches should be to enable all of this from happening. And that's it.
Great. We have one question from Slido. Can I ask, around the virtual energy system, how and when will real-world live data be built into the system? ? Also, are other things like the Energy Systems Catapult Living Lab being used? Are other energy vectors being considered? Lots of questions in that one question. I appreciate that.
I'm sorry, so the first part was about timeline kind of thing, I think?
Was about real-world data being built in.
So today we already have access. So this is ESO, right? So we already have access to a lot of that data that is coming from the system. We haven't yet built it, connected all the different ones, but it's already happening. Our timeline is anywhere between 3 to 5 years, so we can actually start building the very first centers. How we are going to deliver it step by step, the hope is that once you start getting all the networks connected, so that's why you're doing the backbone out of those 3 use cases, it will create enough value for everybody else to come along. What was the second question?
Second part of the question was, are things like the Energy Systems Catapult, the Energy Systems Catapult's Living Lab being used?
Yeah, so to answer that and to add to the first question, in the development of one of the use cases that Carolina talked about, and indeed all of the use cases, they're at a point where imminently, and we're talking in the next couple of months, we're starting to develop and bring in that live data and starting to make and demonstrate the value in why and what we will use the virtual energy system for. In the development of the common framework that Arup, supported by the Energy Systems Catapult and Icebreaker One, are doing, Energy Systems Catapult are involved. So we're pulling through all the knowledge and experience that both they and Icebreaker One have in developing the common framework with ESO.
Okay, there was a last part to that question, but they got 2 out of 3, so I'm going to move on to a different question. How can the community be more involved in these use cases or access these results? Are these projects being run as innovations, or?
Yes. So right now they are being run as innovation project, and because of that, we do have an obligation to disseminate. So please reach out to the email address that was there, but in any case, if you do go into the ESO website and head over to innovation, you will have access to videos, slides, and all sorts of information around our projects.
This email address here, if you want to get involved.
And we will pretty much redirect you to the ESO website where all these projects are being published, or the VES website as well, actually.
So the last part of that last question was, are other energy vectors being considered? And can you tell me what an energy vector is?
Yes. So an energy vector is how you transmit energy from one point to the other. Vector is literally like. So absolutely, yes. some of you are aware of the fact that ESO is transitioning to something called future ESO, because we don't have a name for it yet. But the future ESO is going to include not just electricity, but gas, hydrogen, and a lot of other things that are above my pay grade right now to know about, but it's coming. So a lot of the work that we're doing right now is around whole energy system, meaning we are thinking of ways of integrating gas, electricity, and actually a few projects, digital twin projects that we're taking forth through the Strategic Innovation Fund are looking at gas and electricity together. So what data needs to be exchanged between gas and electricity to optimize energy flows while ensuring that we hit decarbonization targets as efficiently as possible.
Excellent. That was the last of the questions. Well, I would like to thank Carolina and Simon so much for your presentation.
Thank you
very much. Let's give them a round of applause.